We've already observed that an equivalence relation, which has these three properties, the reflexive, symmetric, and transitive, has this amazing ability to partition a set. What that really means in a nutshell is that all of our equivalence classes are going to be distinct, non-empty, non-overlapping subsets of A, the thing that we're imposing the relation on. And when we union all of those classes together, we're going to get back the original set. So now we're going to think briefly about why that is. So an equivalence relation R on A, so we're imposing a relation on a set A, and if it has the reflexive, symmetric, and transitive properties, then it's called an equivalence relation. If it is an equivalence relation, we have these things called equivalence classes. And we denote that with the square brackets, X, and that's the set of all elements in A equivalent to or related to X. The way we've written that before is as follows. We've basically said that X is going to equal the set of all other elements, or potentially X can be related to itself, such that the ordered pair X, Y is an element of that relation. So the features of this equivalence relation. First of all, A is going to be partitioned, meaning, again, these three things are what's required to be partitioned into subsets of A. X1, its equivalence class will be one subset of A. X2 will be some equivalence class, which is a subset of A. And we may not necessarily have two of these. With the even-odd numbers example, that's one possibility, but there are lots of other ways that we could split up a set. We could, if we were thinking about relating family members, then P could be the set of all people in the world, and then each individual equivalence class would just be a family within the United States, within the world, and if we unioned all those families together, we would get all the people in the United States. So we're going to have, in general, n of these. And n just denotes the number of distinct classes. Now, if any two classes are equal to each other, we don't need both of them. If two sets are equal, then we only need to list that set once. That's the rule of working with sets. So here's what's going to happen. There's not going to be any empty classes. So you can pick any equivalence class you want, and it's not going to be empty. Here's why. If something has the reflexive property says that X is related to itself. And since we're dealing with equivalence relations, we know that that equivalence relation will have the reflexive property. It will have an element. Each element is always going to be related to itself. Well, if X is related to X, what that means is that maybe I won't use X. Maybe I'll use A, comma A. That's an element of the relation. So the consequence here is that if I look at the equivalence class for A, for any value of A inside of my capital A set, then that is at minimum going to contain itself. I don't know, some of these may just contain only one element, or they may all only contain one element, but at least I know that every equivalence class is at least going to contain the element of the equivalence class. And so that guarantees that none of these equivalence classes are going to be empty. Now, why is the overlap going to be empty? In other words, if we try to intersect two of these, why will they always be empty? So think in terms of the evens and the odds. When we intersect the equivalence class of 1 with the equivalence class of 2, where the equivalence class of 1 is a set of all odd numbers, the equivalence class of 2 is a set of all even numbers, if you intersect them, there's nothing in common. This actually kind of happens in part because of the symmetric property. And why does that happen? Well, symmetric says that if X and Y are in the relation, then that also guarantees that if you do have the symmetric property, that same ordered pair, but flipped elements will also be in that relation. So what that means is that X is equivalent to Y and Y is equivalent to X. that means that the equivalence class for x will, well, because it has the reflexive property, will contain x, and it's related to y, and then it's going to have some other stuff in here. And then the equivalence class for y is going to contain, well, it's going to contain itself, it's going to contain x, and it's going to contain perhaps myriad other elements. So these two are going to be equal. Now you might say, but what if the other elements don't agree? And that's the beauty of transitivity. Transitivity says that if x and y is an element of the relation, and this is a big if, right? This is not going to be true for every single set of ordered pairs. It's just going to be the ones where x relates to some other element, and that other element relates to some third element. Then we're guaranteed by transitivity that xz is also an element of that relation. So if it is the case that x is related to y, and then we find out that y is related to some other element, and you're like, well, wait a minute, that means that z is going to be inside of this class over here. Well, we can also say that it's going to be in the equivalence class for x. And the reason we can say that is because it has transitivity. So if x is related to y and y is related to z, then that means x is related to z as well. So that means x is going to pop in here. So as long as x and y are related, y can be related to a bunch of other elements, but by transitivity, that guarantees that x is also related to it. So as we continue to populate the equivalence class of x and the equivalence class of y, they are going to contain all the same elements, and therefore they're going to be the same equivalence class, which means, well, sure, these, when you intersect these, they have all the same elements in common, but if the two sets are equal in the first place, then they are the same set. Finally, because of these two things here, the consequence is that if every single element is going to belong in some equivalence class, right? At least in itself, an element is going to be in its own equivalence class. And because they're non-intersecting, and every element will be in some equivalence class, when you union them all together, you're going to get the set A. And what this will look like is a picture. If this is my set A right here, and what I've just done is I've broken this up into the equivalence class for x1, the equivalence class for x2, and so on. Any equivalence class that's repeated. Note that these subscripts do not have anything to do with the numbers in the set A. It's just equivalence class number 1, equivalence class number 2. So we're going to have n of these in here, and these are assumed to all be distinct, that if there were two equivalence classes that were equal, you just picked one of them and called it x1, and if there were a bunch of equivalence classes that were equal to x2, then you would just call them all x2 and eliminate the duplicates. And so we've effectively taken A and we've partitioned it into these distinct groups. So hopefully you can see some applications where this would be really, really important, at least at the architectural level of computers. Files, if you're thinking about files and having files in distinct locations, any situation in which you want to take some group of things and break them up into their own entities, and it's very, very important for you, in maybe perhaps some context, to make sure that you do have a partitioned set, or think about a partitioned hard drive. It breaks it up into non-overlapping pieces. Partitions are incredibly useful. If a relation doesn't have these three properties, all we can say is that it's not an equivalence relation. It doesn't mean that it's not a useful relation. It just does not have this impact.